All right, so I went over it very fast, and but I gave at least the intuition for how to get around this thing. And so if you do it right, and if you spread out the rewards in the right way, you get something that's incentive compatible. Let me just very quickly mention this lower variance thing. The point here is this fruits is a completely different mining process, and I can use a completely different difficulty level. Difficulty was needed to be high for consistency. But the point is, for doing the rewards, I can use these things, I can use a much smaller difficulty level. So I could have each block containing 1,000 fruit. Okay? And that means that now fruits are mined 1,000 times as often as blocks. I can get fruits every second. Okay? And therefore, now the rewards come much more often and you have much smaller variance. In fact, we implemented this thing, and by doing something like this 1,000 times higher, only adds a very small fraction of, kills up a very small part of the block. Because fruits are very small, yeah?
Something very basic, like I have a block.
Mm-hmm.
Now, many people can mine fruits over that block, or is it just one fruit per block?
Many people can mine a fruit over that block, from that block, yeah. The blocks now, the only thing they're used for actually is as a clock. It's a clock that's kind of unpredictable as a way to sort of start off the other mining process. Okay, let me move on to this second part. I don't have that much time left, which is sleepy consensus. I'll try to do this fast. So sleepy consensus was trying to answer the question, do we need to do all this wasteful work? Remember, in Nakamoto, we need to do this proof of work. And I mentioned to you before that this was needed because there's an impossibility saying if you want security in a permissionless setting, you cannot do it without proof of work. Right? But this guy is tired and he doesn't want to waste all this energy. And so like 6 months ago or so, the amount of energy that's wasted on Bitcoin alone is roughly 10% of the solar power in the US. It's kind of a lot. Okay? So it's not great that we're wasting all this energy. But as we said, if I want a truly permissionless blockchain, we cannot get around it. We need to do all this wasteful stuff. But in many applications of blockchains, we don't need to be truly permissionless, right? In many settings, it's okay with a permission blockchain. We have all these like 1,000 banks that would like to get a blockchain among them. In those settings, we have a public key infrastructure in place. So in those applications, we already have a public key infrastructure. We want many of the features of a blockchain, in the sense that we want it to be scaling to lots of players, but we don't need anybody to join. So we want it to be scalable, and maybe we want extra robustness properties that blockchain have that not everybody is there all the time. And the same thing is with proof-of-stake cryptocurrencies. In proof-of-stake cryptocurrency, when you already have a bunch of currencies being sold, the keys that the money in the system correspond to public keys, that they set up a public key infrastructure. So we have a public key infrastructure already. And in those settings, maybe we don't need proof of work. And indeed, that's what all these attempted solutions to proof of stake come up with these type of protocols. In fact, in a public key infrastructure, classic consensus just works, right? That's what it was designed for. But the issue here with those classic things is, as we said, they're only kind of for 10 people, 10 nodes usually, and they don't scale very well. Not only they don't scale very well, it's very complicated to implement these things. Okay? And as far as I know, there are very few real implementation of the Byzantine versions of these consensus protocols. And they require an exact knowledge of how many players are around. And as I said, for many of these applications, it's actually not so good. Like even in a proof-of-stake blockchain, not everybody's going to be there all the time. I go down to the subway, I like leave the network, so it just doesn't apply. So the idea then is, can we just take Nakamoto's protocol? It's so simple, right? It's dirt easy to implement. Can we just remove proof of work from this thing and get us a consensus protocol in kind of a PKI setting that works? And that is what the sleepy consensus is. So we take Nakamoto's protocol, we're going to remove consensus, we're going to remove proof of work by relying on a public infrastructure and maintain the scalability to make it as scalable as Nakamoto's protocols, it's thousands of nodes, and as robust in the sense that we don't need to know how many people are actually around. So that's the goal, and that's what we achieved. So on a very high level, the idea is the following. So the idea is that what does proof of work actually do here? So the right way to think of Nakamoto's protocol is that this proof of work is every 10 minutes electing a leader, and the leader is pointing out what is the longest, what is the current chain, and what transactions get added, right? So it's every 10 minutes I'm picking a guy, Yoram gets to decide what is the chain at the moment and what are the transactions I'm adding, okay? Then I'm selecting run next 10 minutes, and he will select what transaction get added, okay? And that's the only thing that this proof of work is actually doing. It's selecting some guy that decides what transactions get added. So we'd like to emulate this thing without proof of work, leader election. And the idea is very easy. Let's do exactly what Nakamoto does, but let's restrict the puzzle space so that players only get one query for a puzzle in every round. So let's say that every second I need to, I can mine for a puzzle solution. But the only thing I can mine for, that's okay for me, because now I have a public key, is one particular solution. So each guy gets to try one solution per round, per second. Okay? And since we have a fixed set of players in a PKI, everybody can check. If I submit a solution that's not with my designated solution, then we reject it. Does it make sense? So now we don't need to do any mining because I'm only allowed to make one try per second. Yeah?
So how is the public key infrastructure helps? If we go back to the original problem, we had the problem of an adversary breaking word identity.
Yes, so what I'm saying is, that is unavoidable. In that setting, when you have an attacker making more identities, you have to use proof of work, right? Now I'm saying if I have a public infrastructure, that's what it's helping, because now we have a preset max bound on the number of public keys out there. You have to do that in the beginning, yes, yeah. So in the context of banks or in context of proof of stake, we have some original stake that's set up, you have some keys that's set up in the beginning, everyone knows what they are, and that needs to be set up in the beginning. So that one makes it different, and we're going to leverage that to get rid of it. Because otherwise it's impossible, otherwise we showed it was an impossibility. Okay, so a bit more concretely, before it was like this, I'm hashing the end, transactions in a puzzle. What I'm going to do now is I'm going to hash the name only. So I'm going to hash my name and a clock time. Okay? So at each time step, I'm going to hash my own name. And if this is smaller than D, I was the winner. And if I'm the winner, I get to add some transactions. And what does it mean to add transactions? I'm signing, now using my secret key, the end of the chain, the new transactions, and the current clock. And now everybody can check that this was actually, I was allowed to extend it because I was the winner. Run. Question?
So if you only allowed once, then no one is smaller.
Nobody can win in this time step. Yeah?
The only one, so what happens if you just take the lowest one?
So there could be I don't care. There could be, same thing with proof of work, right? Some steps, sometimes seconds, nobody does it. Every 10 seconds, somebody wins.
This would slow down.
No, it's the same thing. I'm setting parameters in exactly the same way. I'm setting difficulties so that every 10 minutes, somebody wins. Most time steps, nothing happens. Some time steps, there are two guys winning. That's not an issue, right? We can get forks, and we're going to be dealt in exactly the same way. Okay? Sorry? Very good point. So here I'm assuming that there's a global clock, and I will need it. Okay, I will need that people have roughly synchronized clocks. These clocks can be off by 10 seconds, but I assume that people's clocks are pretty close. You can actually make that assumption weaker, but let us not get into that now. I think it's pretty fair to assume that our clocks are within 2 hours of each other. That's all we need, actually, right? Okay. So the difference here from before, note I'm putting into the hash function the previous thing, new transaction this. Now I'm just hashing my name in a time step. and then I'm signing the previous thing and this and this, and the solution. The reason that I don't put in the end of the chain into this thing is because otherwise people could continue mining, they could try different ending points, and we don't want to allow that. So instead here, the only thing you're putting in to check if you're the leader is your name and a timestamp. So, and then when you're a winner, you put it up there, and that's it. This doesn't quite work, because if I'm elected leader, I can potentially reuse these blocks multiple places. There is just one simple fix that the only thing you need to add here is that in the chain, you require these time steps to be strictly increasing, number one. And the second thing is I should not accept time steps into the future. So when somebody sends me a block, if they send me a block of something that's more than 2 hours into the future, I reject it. Okay, and that's it. And with these two things, you can now do this analysis, which is kind of complicated, to show that this is actually going to be a good consensus protocol. It satisfies the same 3 properties as Nakamoto Consensus. And not only that, it works even in a setting where you don't know how many players are actually around, as long as a majority of people are around actually are honest. So can we take it in? I only have the last slide because 1 more minute. So to summarize, we've shown you this new blockchain protocol that doesn't have any proof of work. It's essentially just Nakamoto's protocol, where we kind of surgically remove the proof of work and relied on a public infrastructure to instantiate this thing. And you can provably show that this gives you a classic consensus protocol using a very different method than all previous consensus protocols. They use much more complicated things. So it's very, very easy to implement. In fact, we have this open source implementation that's going to be released very shortly, maybe in a week or two. And it retains the robustness property of Nakamoto's protocol, which is this thing that it works no matter how many people are actually showing up. Right? We don't need to know how many people are there. As long as the majority of the people showing up are honest, it's still robust. And this has these several applications. For instance, permission blockchain, or it can be used in a proof of stake protocol. So we have some ways of, in a proof of stake protocol, you need to have some slightly extra annoyances because the set of public keys are changing over time, but it can be dealt with in a pretty straightforward way. But this is the core thing. So to summarize, what I've been discussing today, it's first just Nakamoto's consensus protocol. Right? I went over the consensus protocol that Nakamoto came up with. It's a beautiful, extremely simple protocol, just basically 2 lines of code, kind of magical. And this very simple protocol, we showed satisfied very strong robustness properties. It satisfied the robustness properties you want of normal state machine application, with some caveats. Number one was that we assumed that a majority of the computing power that is participating in this protocol is held by honest players. So that's the difference with the classic model. And the second thing is that puzzle difficulty needs to be appropriately set. Right? So if the puzzle difficulty is set correctly, so that blocks are mined much slower than network delay, in that case it's secure. But we had a few different caveats. The first one was that it really needed to be slow, because otherwise it was not secure. It wasn't fair, right? There are these selfish mining attacks that we'll hear much more about shortly. But we could overcome them using the fruit chain protocol. The fruit chain protocol, note that it just used the underlying blockchain kind of as a black box, and on top of that built something that it was a way to amplify quality. So we start off with something that just has like some minimal chain quality, and we could amplify it up to something that has optimal chain quality, optimal fairness. And once you have optimal fairness, you get incentive compatibility. And finally, Nakamoto's thing relied on these expensive proofs of work, but we showed a way to surgically remove it in a setting where you have a public key infrastructure in place, and then we can retain a lot of the scalability properties of the blockchain and also robustness properties just without having the proof of work. And as I mentioned, we haven't discussed these confirmation times. Later on tonight at 4:30, I'll show you this new protocol called Thunderella that, again, is going to be based on a similar principle of we're going to use Nakamoto's protocol underlying and then build something on top of it that just makes transactions confirm instantaneously as long as things are good. And otherwise, the blockchain is kind of they're underlying to help us to enable it. So that was it. Thank you.